Okay, so here we go, Monday morning, a little bit of administrative stuff. Again, our next exam is going to be on Friday, the 8th of November, and it covers up through Chapter 7, although we're talking about Chapter 8 type stuff now. Oh, same as last time for the people who are off campus. I don't think there's any changes. The only thing I forgot to announce last time was bring some paper, because I know some people, they were just like barely squeezing their writing onto the, I didn't even give you a blank background last time. I remember I had used paper for the people in class. So that's coming up. The other thing is on the lecture that I did on Friday, it talked about a homework that was going to be due coming up. And I just moved that homework date from like Monday the 4th till Wednesday. Give you another couple days to work on that. Okay, so in Chapter 8, what we're working on, I love Chapter 8. There's definitely some new stuff that's going to happen here. So we started off, the whole purpose of Chapter 8 is how to analyze Group 2 spatial mechanisms. So here's one over here. It's a spatial mechanism that has mobility 1, but when we did the equivalent spherical mechanism, we got mobility 2. So that meant that when we go to the toolbox for this, the best we can do is to find equations in 2 unknown thetas. So for example, if this problem statement was for this mechanism given, let's see, there's 5 links. So A12 through A51, alpha 12 through alpha 51. Let's see, where the revolute joints, I'm going to know the offset S1. There's a revolute at 3. Let's see, there's a revolute at 5. It's a 1 degree of freedom device, so I'm going to do that one in a different color. But say I give you theta 5 as the input, and then what we had to find was, see, the remaining joint angles. So there's theta 1, theta 2, theta 3, theta 4. And where the prismatics are, there's let's see, S2 and S4. So that's the problem statement. We are going to be able to solve it. And in general, what we're going to find is there's 8 possible solution sets for those 6 parameters, theta 1 through theta 4 and S2 through S4. We're really nowhere close to solving it yet. But because when we looked at these equations over here, we said the best I could do was to get, it's okay to have theta 5, but the best I could do is get an equation that has 2 of the other thetas. So I can't just get one equation, one unknown, and solve it out. That means that we're going to have to go over here and get an equation in 2 thetas. Now, the way we're going to attack these is we're going to look at the spatial thing and find this equation that has 2 thetas. And no matter what 2 thetas it is, no matter what equation it is that has the 2 thetas, we are going to be able to find a spherical equation that has the same 2 thetas. So for example, it's okay to have theta 5. Suppose over here I found an equation that had theta 1 and theta 2. Oh, well, I'd come over here and I'd pair it with Z512 equals C34. What if I came over here and I found an equation that had just theta 1 and theta 3? It's okay to have 3. Well, let's see. It has 1 and 3. I'd say Z51 equals Z3. Right, that's who I'll pair it with. So no matter what 2 I get here, I will be able to find an equation in those same 2 over there. So where we have to head in this chapter is how do I go to the spatial mechanism and find an equation in just 2 unknowns? And we're not quite getting there yet. So what I did last class was say, suppose I was able to get 2 equations that were linear in the sines and cosines. So one of these 2 equations is going to be one of those cosine laws. And it will factor into this general format where the A and the B's and the D's are all going to be numbers. And what we showed in the last lecture was if I could find 2 equations like this for that mechanism, how would I solve it? And what we did again is we went to tan half angle. So we substitute all these sines and cosines with those expressions multiplied through by the denominators. And we turned these 2 equations that were in the linear and the sines and cosines of 2 unknowns into, here we go, 2 quadratic equations, or biquadratics, where the little a is known in terms of the capital coefficients. And again, the problem statement we did on Friday was given numbers for these parameters, how do I find the values of theta I and theta j that simultaneously satisfy both equations? So we converted it from equations in the sines and cosines to equations that were biquadratic in the tan half angles of those, where these little a's that are through little j's are known in terms of the given big A through big J. And we went through Bezout's and Sylvester's method and saw how it's kind of crazy, but there were 8 possible solutions. So I'm going to kind of skip down through that, and then how to get the, the 8 solution pairs. Okay, so what we want to do today is, if we go back to this case, somehow from this spatial mechanism, I need to get an equation in 2 unknown thetas. So again, if theta 5 is given, I don't care what 2 thetas are in there, but boy, I need to find an equation in 2 thetas such that I can pair it up with one of the cosine laws from the equivalent spherical mechanism and then do Bezout's or Sylvester's method to solve out for the 8 solutions. So what we're going to do is, first of all, just talk about general approaches before we attack this particular mechanism. We're going to look at 3 techniques to generate equations. And again, the equation's going to have to come from the 3D mechanism, because we got a whole toolbox of equations for the spherical mechanism. And those equations, different from over here, is they are going to have link lengths and they are going to have joint offsets. So they're going to be a bit more complicated equations. So we're going to look at 3 different techniques. 2 of these are pretty obvious ways to get equations. We just don't know how to apply it yet to our problem. And this last one's going to be something completely new, this thing called secondary cosine laws. Okay, so to generate equations for the 3D mechanism. Again, right now I'm not worried about what is the particular equation we're going to find for this one. I'm just talking about here are techniques to generate equations that have thetas, alphas, link lengths, and joint offsets. So one technique that's going to be kind of easy is called this projection of the vector loop equation. Oh, okay, I thought I had some more PowerPoint slides there, but I don't. Let's go ahead and look at this mechanism and write down the vector loop, because it only has 10 terms, so it's not as bad as some of the others. So the vector loop equation is going to be S1 times the S1 vector plus A12 plus S2. Let's put another one here, A23. Those 10 terms. I'm spacing them out for a reason, but it would have been nice if I could have gotten 5 on each row, but that's all right. S3, A34, S4, A45, S5, A51. And if I walk all the way around that loop equation, I'm going to get the 0 vector. So again, this technique that we're going to use to generate equations is to take the vector loop equation and just do a dot product onto something. Now, later we have to say, oh, for this mechanism, is there any strategy that might be good of why would we pick something to dot product with? And that's in the future. Don't worry about that right now. For now, just say, oh yeah, I'll get equations. If I decide to take all of this, all of these terms and do a dot product, say with A23. Of course, I know this one's going to go to 0, and this is going to go to 1, and then this one will go to 0 because of what I picked. Fine. And again, when I evaluate these dot products, both of these vectors have to be in the same coordinate system, but I could evaluate this in coordinate system 2, right? And the directions of all those vectors are given in the appendix in coordinate system 2. And I could evaluate this in coordinate system 4. I mean, as long as both vectors are in the same, because the dot product is invariant with the choice of coordinate systems. So again, when I was taking the class, I said, well, fine, I granted this will generate an equation, but I keep looking at that one example that we're going to be doing. We're going to be doing it in a little bit. And how would I decide what to dot product with? And for right now, I'm going to say don't worry about it. Right? We're going to look at that later. But this would get us an equation. Maybe if I'm lucky and I pick the right thing to do a dot product with, maybe I'll get an equation in just two of the thetas. But we're going to see a strategy later on. But for now, I'm just going to say, yeah, that would get us an equation. Okay, the next thing we're going to do, I'm going to erase all the blue here. So we start off, oh, I shouldn't have done that. So I'm just going to take the entire vector loop equation, and the second one we're going to look at in our list is called the self-scalar product of the vector loop equation. Okay, I got to get rid of all these dot products. And again, all we're trying to say right now is that, yeah, if I did this little technique that we're going to do, I would get a scalar equation. I have no idea at all today what the strategy of how I might use this to solve that particular problem, but I'm not worried about that today. We're just trying to say that, yes, this will get us equations. What the self-scalar product has to do, what I'm going to show here is a little different than what's in the book, but it's the same principle. Suppose I decide to take some of these terms and move them to the other side of the equal sign. So I'm going to take these three. I'm going to have minus A34 vector, minus S4 vector, minus A45 vector, and then I can erase all of those from that side. So, okay, that's still the vector loop equation. And we know that the left side is going to have to equal the right side. And then here's what we're going to do. We're going to take the entire left side, and we're going to dot it with itself. So I'm going to have S1 bar plus, I'm going to go dot, 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 A51 bar. And then I'm going to take the right side, and I'm going to dot it with itself, minus A34 vector, and I'm going to skip all the way to minus A45 vector. So I've got a lot of dot products I have to evaluate because I've got S1.S1, I've got S1.A12, S1.S2, and then I have to go, right, A12 dot this plus this. There's a whole ton of dot products, but I will get a scalar equation on the left, and I'll get a scalar equation on the right. Now, again, if I look at the problem that we had for the start of this chapter, I'd say, how could this technique help us? And then, holy cow, I have to decide what terms to move to the other side? Seems pretty crazy. Not worried at all about it right now. I'm just saying that that would get us a scalar equation. Boy, it's, our feeling right now is it's almost like random number generator. I have to try every possible thing. I move all this stuff to the other side and dot product, and maybe I get an equation in two unknowns. We're going to see that there is a strategy coming up, but for now, not worried about it. Just saying, yes, that would get us equations. Okay, the third technique is secondary cosine law. And for the secondary cosine law, we have to tell, a long story. And some of the things I like about the class is, I doubt if you've seen this before, so it's something new. Like one time I taught some kind of numerical methods thing in the undergraduate curriculum, and I'm teaching them how to do a dot product. I'm like, oh, come on, they must have seen that somewhere else. This is going to be something new. So the third technique we're going to show to generate equations from the spatial mechanism is called secondary cosine laws. And to get there, we have to introduce something called a dual number. A dual number. Now the definition is really, it's correct, but it doesn't really tell us much. It says it's two real numbers, one of which is associated with the regular plus one, and the other of the two real numbers is associated with this operation, or this operator called epsilon. So here's an example of a dual number. 4 plus 7.2, let's even make it a float, 4.2 plus 7.2 epsilon. So that's a dual number. Now what's special about epsilon? What's special about epsilon is that epsilon squared equals epsilon cubed equals 0. So, and that's our definition. Wow, okay. And what we're going to do is we're going to start off with how do I add dual numbers, how do I multiply dual numbers, subtract dual numbers, and divide dual numbers. So we're off on this side story, and somehow it's going to lead us to equations and something called secondary cosine laws. Okay, so it's kind of a weird operator. Now, I try to remember, it was in high school when I was, introduced to I was the imaginary, right, where I squared is -1. And I forgot what the story was that the teacher told, but it must have been a really good story. Something you square it and you get -1, and now I'm like, oh yeah, I just accept it like that's normal. So here's what I thought about epsilon. Now I asked, Dr. Duffy would invite over these, especially they were from Europe, these mathematicians that were like world class, and he was giving us a lecture on something, and I was sitting in the back, and I asked a question, or I said, hey, here's how I think of this epsilon sometimes. Because I work with computers a lot, I think of epsilon like, oh, it's like a really small number such that, when the computer squares it, it rounds and it goes to 0, it vanishes. And all I remember the response from the mathematician guy was a very loud no. And he went on, and I don't remember the rest of it. I just remember the no. It's like, it was like my hair almost blew back. It was no. So violently no. Okay, so if that's not the case, I'm going to just sort of live with it and say I got this weird operator. How are we going to write these dual numbers? I want to make sure I show some of the notation and stuff. Okay, so I'm going to show a dual number is a hat. It could be a plus epsilon a naught. So in this case, right, the a would have been 4.2 and the a naught would have been 7.2. So let's go ahead and take two dual numbers, and we're going to make sure we know how to do addition and multiplication and all that. So addition is going to be pretty easy. We're not going to have any real strange results here. What we're going to find is that if I add two dual numbers together, I get a dual number. We call the first part the real part, and we call this part the dual part. So the real part was just going to be a plus b, and the dual part is the stuff multiplied by epsilon. So no magic or anything hard to remember there. What about if I was to subtract? A minus b would be, the real part would be a minus b. Well, it's just an a hat minus b hat. Right? The real part is a minus b, and the dual part would be a naught. So that's no big deal. And let's go ahead and define multiplication. So if I take this dual number times that one, I'm going to have a plus epsilon a naught times b plus epsilon b naught. And let's see, we're going to get a real part that's equal to ab. And then I've got a dual part. I've got what? A naught b plus b naught a. And then there's an epsilon squared times a naught b naught. But remember, epsilon squared went to 0. So we haven't done anything on the multiplication that we're not used to doing in multiplication. We just took advantage of the fact that epsilon squared was 0, so no problem with that. Next thing we have to look at is division. So what if I have a divided by, or a hat divided by b hat? So I've got a plus epsilon a naught. And what we're going to do is to sort of multiply. I shouldn't probably use the word conjugate because that's kind of from, imaginary numbers. But I'm going to multiply this by b minus epsilon b naught over b minus epsilon b naught. So in the numerator, we're going to get a real part of ab. And we're going to get a dual part, a naught b minus a b naught. In the denominator, we're going to get b squared, and then I've got I got epsilon times bb naught, and then I've got epsilon times minus bb naught, so the denominator just goes to b squared. So I wind up with, let's see, ab over b squared is going to be a over b plus epsilon A naught B minus AB naught over B squared. So no magic or anything. Okay, what if I was dividing by my B plus epsilon B naught? What if this B was 0 and B naught was 5? Dr. Duffy called that a pure dual number because it only had a dual part. It didn't have a real part. And what we're going to say, because the problem is if this B goes to 0, right? So what we say is that's not allowed. It's not defined. You can't divide a dual number by a pure dual number. Not going to work. In a way, I'm kind of surprised that we just don't even consider it because, right, this goes to infinity, and we know how to handle stuff at infinity, but that's okay. We're just going to, at this point, say it's not defined. Okay, so we got these crazy dual numbers. Let's see if there's anything else I missed on them. That's why I brought my book today. Oh. Okay. We're going to look at functions of dual numbers. So again, definition's real easy. Two real numbers, one of which is associated with 1, the other is associated with epsilon, where epsilon squared and everything is 0. Addition, multiplication, all that's pretty standard, nothing real magical. But suppose I had some function. I'm going to go ahead and use the one that's in the book so that I don't mess up today. Suppose I've got some function of x, and the one we're going to use as an example is 3x squared plus 2x plus 7. Is that right? Yep. And I want to evaluate that when x is equal to 5 plus 2 epsilon. Okay. So we're not going to do any magic. I'm going to say it's 3, 5 plus 2 epsilon times 5, squared, plus 2. So we're not doing any magic. We're just going to, plug a dual number into a function and see what we get. We're going to get a dual number as a result. Let's go ahead and work this out. I'm going to have 3 times, let's see, I'm going to have 25 for the real part of this product. And the epsilon, I'm going to have 10 plus another 10. So it looks like 20 epsilon, if I did that multiplication right. Okay, and then over here, I've got 10 plus 4 epsilon plus 7, and we'll keep going. I've got 75, 85, I got 92 for the real part. And the stuff multiplied by epsilon, I've got 3, I got 60, 64. Okay, let's see if that matches what was in the book. Yep, 92 plus 64 epsilon. So no big deal. If I have a function of this one variable x and I want to put a dual number in, no big deal. No big deal at all. We're going to show another way to evaluate this, so using Taylor series expansion. Okay, using Taylor series expansion, which remember is just an approximation. So imagine I had x versus, f of x over here. And if I was to plot that, imagine I had that. And how does Taylor series expansion work? It says, well, if I was to evaluate at some value x, and then, I guess my curve's okay here. I'm going to go some distance. This will be x plus delta x. Okay, this is the function evaluated at x, and the value up here is the function evaluated at x plus delta x. And the way Taylor series expansion works is it says, well, the function evaluated at x plus delta x is probably, because delta x is usually pretty small, it's probably going to be close to the value of the function at x. Yeah, it is pretty close. But, let's see, what are we going to add here? What if I add, let's see, right? This distance here is delta x. What if I take, the slope here? What if I take slope evaluated at x. I call x my expansion point, and I multiply that by delta x. So what is that? Well, the slope evaluated at x would be at my expansion point. I go ahead, and the slope is rise over run. I've multiplied it by run. I'm going to get that rise. So what this term does is it says, yeah, the value of the function at x plus delta x is close to the value at the function at x, plus whatever the slope is at x, times how far, I tweaked it away, delta x. And it's sort of imagining that there was a straight line that was tangent to the curve at that point, and if we treated it as a straight line, But in Taylor's series expansion, it kind of continues and says, well, that's kind of an approximation. So if we want to continue with this, I got to make sure I get all the terms here, that it's going to be the second derivative evaluated at the expansion point times delta x squared over 2 factorial. And then it would kind of keep on going. I guess it would be the third derivative evaluated at the value x at the expansion point times the delta x cubed over 3 factorial, and right, it goes on forever. So the Taylor series expansion, again, it says, yeah, the value of a function at x plus delta x is close to the value of the function at x. But here I'm going to take my first derivative term and then my second, but I have to keep going forever. So we're going to apply this now to dual numbers. Okay, so let's see. I'm trying to think of the best place I could write it. I wish I left a little more room there, or here. Any of those would have been good. So what we're going to say is I've got this function f of x. It's on the other board. And I'm going to go and evaluate it at, let's see. I'm going to evaluate it at a plus epsilon a naught. So if I apply this Taylor series expansion, I'll try to write it up here. I'm going to say that the function evaluated at a plus epsilon a naught is going to be close to the value of the function evaluated at a. Okay. Then I'm going to take the first derivative of the function evaluated at my expansion point, x equals a. Right, so that's the slope at my, again, I'm thinking of the expansion point, which I called x here. I'm calling it a now, times how far I tweaked it. Well, I tweaked it by epsilon a naught, right? That's my delta x in this example. I'm trying to make sure I don't mess this up here. Yep. And then I could keep going, right? I could say the second derivative evaluated at my expansion point, but then it's times how far I tweaked it, epsilon a naught squared over 2 factorial plus dot, 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 dot. And guess what, right? Epsilon squared is 0. This term would have had an epsilon cubed. Those terms, because of the definition of epsilon, are 0. So when we did this Taylor series expansion down here, and depending on how many terms or how many derivatives, it's always an approximation, and to get the exact answer, you'd have to keep getting an infinite number of terms. But when we put dual numbers into these functions, it's not an approximation. It's dead on. Holy cow, let's apply that to this and see what we get. Okay, so I'm going to say that the function evaluated at 5 plus 2 epsilon, and here's my function. So it equals the function evaluated at a. 25 times 3 is 75, plus 10 is 85. Oh, so that's 92. And then what comes next is the dual part. That's what's times epsilon. And it says evaluate the derivative of this. So df dx is 6x plus 2. And it says evaluate that at the expansion point. df dx evaluated at x equals 5 is 32. Okay. and if I go back here, what did I mess up here? Epsilon A naught. In our case, A naught was 2. Right? That's how far I tweaked it. That's my delta x is 2 epsilon times, here, the derivative evaluated at the expansion point. It's dead on. It's not even an approximation. Now, you'd look at this and you'd say, well, why would I ever bother with that? Because this was pretty easy. But what if I had like an equation to the x to the 40th power or something? Holy cow. It'd be a lot easier to take the derivative approach and use the Taylor series expansion. So for dual numbers, this Taylor series expansion is the exact result. There's no approximation for just that one derivative term. Okay, so now, so this equation here was real important to us. If I have a function of one variable x, well, that's what we had down here, and I want to evaluate it at this dual number value so I'm thinking of A as my expansion point, epsilon A naught was my delta x, right? That's how far I tweaked away from the expansion point. And applying Taylor series expansion, boom. So it's a function at the expansion value plus the derivative evaluated at the expansion point times how far you tweaked it. You tweaked away from the expansion point by epsilon A naught. So it seems a little weird, but it works, and it gave the exact answer. Okay, so what we're going to do next, right, and we're supposed to be doing, group 2 mechanisms, and we're not anywhere near it at the moment. We're just talking about crazy new stuff. Okay. Oh, here we go. Let's do another function. Instead of f of x, let's do g of x. We're going to get a new function, but we're still going to, look at that kind of an application here. Suppose I had a function of one variable, and that function was, I'm going to use the one in the book so that I don't make a mistake, cosine x plus 3 sine x. And again, it's pretty much applied to x's in units of radians, so that if I put in some number for this, I'm going to, get a number. I can get my calculator and calculate them all day long. What if I was to put in for x a dual number? So let's see, we are going to use 2 plus 5 epsilon. Wow. I don't know what to do except for the Taylor series thing. That's my only way to attack this one. I don't know how to, like last time we had x squared plus something, and I just did a little bit of multiplication and all, but I don't know what to do. Well, I can do is the Taylor series. This is my expansion point, and that's how far I tweaked it. So it's going to be the function evaluated at 2 plus dg dx evaluated at x equals 2, that's my expansion point, times, how far I tweaked it from x, or from the expansion point, 5 epsilon. So, hey, I can do this. So the real part is going to be, what, cosine of 2 radians, whatever that is, plus 3 sine of 2 radians, so some number. The derivative of this is, well, let's put the 5 epsilon out front here. So the derivative is what, negative sine of x, and then it would be plus 3 cosine x, but it's evaluated at the expansion point. And again, I don't know what the numbers are going to work out to be. Oh, they're in the book. Looks like 2.31 minus 10.79 epsilon. I don't really feel like I have a good geometric understanding of what's happening here, and I'm not even worried about it today. Just saying, yeah, I had a function of one variable, and I want to put a dual number in. Boom, it's that Taylor series thing. All right. We just apply that. Okay, so what we're going to do next is say, what if I have a function of 2 variables? So like some function of x and y. and what happens with the Taylor series expansion. So let's see if I got an example in the book. Oh, that's a terrible example, but that's okay. Yeah, I wanted a simpler example to begin with, but it's okay. So suppose I had this function of x and y, and it was 4x squared cosine of y plus 3x sine of y. Okay, what does Taylor series expansion look like if we have a function of two variables? So what you want to sort of visualize over here is something a little bit different. Debating about how much of this to erase. Okay. So think of that as x and y, and this is the value for x and y, and you're going to get a surface. You're going to get some kind of a surface up here. Right, so you go to a value of x, y, and you go up and you get a point, and I go to this value of x, y, and I get a different value. So it's going to be some kind of a surface there. Okay, so what is the Taylor series expansion? It's sort of like saying, I'm going to go over here and call this x and call that value my y value. And then I'm going to go over here to an x plus delta x. So we've tweaked it by delta x. And I'm going to go over here to a y plus delta y. So again, we've tweaked it delta y. So so here's the xy value, and we go up and we get a different point on the surface. So what does Taylor series expansion say, how to sort of approximate that? So here's what comes out. It says, if I can get this right here, the function evaluated at x plus delta x and y plus delta y is going to be close to the function evaluated at those expansion points. Then I'm going to say, wow, in the x direction, I tweaked it by delta x. So in the x direction, I tweaked it by delta x. So there's been a change. So basically what I'm going to do is I'm going to get the slope. I'm going to say it's df dx evaluated at the expansion point xy times delta x. What that's going to do is say, think of it tangent to the surface that was out here. There was a line that's parallel to the, well, it's in the xc plane or the xf plane. And I'm looking at the slope evaluated at the expansion point. And when I go how far I tweaked, that's how much, think of the point over here, how much it rose. And then what we're going to do is we're going to look at it from the point of view as if, how far did I tweak it in the y direction? It's going to be df dy evaluated at the expansion point. And what that's doing is it's saying, well, think of it in this direction. I changed the y a little bit. What was the slope at the expansion point? And if I multiply by delta y, I'll get how much that changes. So we're doing that approximation in both directions. And then in Taylor series, I need to have these other terms. I have to have these terms based on the second derivatives, and they're going to have like delta x squareds and things. And I'm not going to write those down for one thing because I don't remember the regular Taylor series expansion. And because when we put dual angles in, all those terms are going to go to 0. So if I was to write this, the function evaluated like this, I'd say, well, it's going to be the function evaluated at the expansion point. So I'm trying to say that my expansion point was AB. I tweaked the A by epsilon A naught, and I tweaked the B by epsilon B naught. So then I'm going to have plus how far I tweaked it in the x direction times, well, I guess I should have put partials here, right? Partial f, partial x evaluated at x at the expansion point. And then the next term I've got is how far I tweaked it in the y direction, epsilon b naught, times the partial evaluated at the expansion point. And then there would be other terms expected in the regular Taylor series expansion, but because of the epsilon squared going to 0, they disappear. So if I have a function of multiple variables, so that's kind of an important result for us to have. So we're going to apply that over here. So it says the function, we're going to evaluate this according to, well, we'll do what was in the book, 4 plus 2 epsilon. And what was the other one here? 3 plus 5 epsilon. And again, we're just doing an exercise, right? This isn't helping us at all to solve those mechanisms, but we're just learning about dual numbers and how to add them and subtract them and multiply them, divide them, and how to evaluate functions where you put dual numbers in them. So according to our result, it says that's the function evaluated at when x equals 4 and y equals 3. And then I go 2 epsilon. That's how far I tweaked it in the x. And then it's the partial of the function with respect to x. Evaluate that partial at the expansion point. So I'm going to have 8x squared cosine y plus 3 sine y, evaluated when x is equal to 4 and y is equal to 3. And then, how far do we tweak it in the y direction? Times the partial with respect to y. 4x squared will be a negative sine y plus 3x cosine y, evaluated at the expansion point. And if we plugged all those numbers in, you'd get whatever, you'd get something plus epsilon times something, and the somethings are in the book. So it seems a little weird. And plus, I mean, it seems like we're just making this up or whatever, but I mean, we don't see the purpose of it, but it's going to be coming. It's going to be showing up. And I'm checking the clock because we got 12 minutes, or no, it's 12 minutes past the hour, so we've got 8 minutes left today. So here's where we're going to be going with this. We're going to introduce something new now called, like we talk about dual numbers, we're going to introduce something called dual angles. Dual angles. Dual angles. Oh my goodness. So what are we going to write as an example of a dual angle? Here's one. Here's another one. Okay. And right, I mean, it seems a little suspicious. I got thetas and alphas, and we've been seeing thetas and alphas, and there is going to be something suspicious happening here. But at the moment, just don't even worry about that connection. Just say that this is the real part, and this is the dual part of what I wrote down here. And this is the real part, and that's the dual part. And then you think about this dual number, though, and when you start going back to what we're doing with our robots, wow, everything that describes a link is in there. Remember what a link does is it maintains the relationship between the two joint axes, like in this case S2 and S3. And what do we care about? The perpendicular distance between them and the angle between them. Wow, that dual number is got all that in. And look at this dual number. For the simple joints, prismatics and revolutes and cylindrics, yeah, there's your joint angle and there's your joint offset. So the dual number is representing all this. This dual angle is what we're going to call it. And then I kind of worry about units, but I'm not going to let it bother me. But right, if I was doing that, this would be dimensionless, and that would have units of length. And dimensionless would, I already had epsilon, so seems kind of flaky. So we got 5 minutes. I'm going to do the major hand-waving part of the entire course. Okay. I wonder if I underline this sentence in the book. If so, So we're not going to like, we only got 5 minutes left. We're not going to like prove this or whatever today. I was hoping I had this underlined, and I do not. I'm amazed. I thought I had this underlined, but I do not see it here. Here's what we're going to do. We're going to take those dual angles, and let me open up the appendices. Okay, that mechanism that we've been looking at was a 5-sided. It was a 2 cylindrics and 3 revolutes. So let's go to the 5-sided. So I go down here and I'm looking for the pentagon, pentagon. Here we go. So I got my toolbox, has all these equations. And especially I'm always interested in the cosine laws because they have 1 less theta. And I got these subsidiaries. I'm not going to worry about the polars right now. We're going to look at these guys. And what we're going to find is that we are going to be able to take these dual angles, substitute them into these equations. And again, we're not proving this today because we only got a few minutes left. We're going to substitute whether a fundamental or subsidiary. And we're going to claim that whatever we get is going to be valid equations. Holy cow. And that's what's going to be called the secondary cosine laws. Right? Because these are cosine laws. When we put dual angles into them, we get secondary cosine laws. The proof of that is utterly amazing. So let's go to our notes. This is due to a Russian fella, Kotelnikov. And I think I got the right picture. I got the right Kotelnikov. So it was around, what was the year this was taken? About 1900, something like that. And plus, what did this guy do in his normal, day-to-day life? But he proved this, that if you take these dual angles and put them into those, we know the cosine laws are valid. If you put those dual angles into those cosine laws, you're going to get valid expressions. Holy cow. Let's see, I thought I had a year on that. I thought it was about 1900. And he called this the principle of transference. So the principle of transference, I've got a paper here, is all about proving that. Again, he wrote it around 1900, and it was in Russian, and it was like real hard to understand. So here's the paper that I linked to our class webpage from 1992 that Dr. Duffy did with Jose Rico. So Jose Rico was one of Dr. Duffy's PhD students. He's pretty brilliant. He's smarter than I am, and he teaches now at this time he taught at the Institute Technology of Celaya, so in Celaya, Mexico, and then now he's at University of Guanajuato. And it's not in Guanajuato, it's right next to it, a little town. Can't believe I can't remember the name. So what they did is they went back to Kotelnikov's paper and then tried to present in English. And so how many pages we have here? 13 pages of fun. Let's see, the history of the principle is interesting. Okay, it was originally proven by Kotelnikov in the latter part of the last century. Indeed, Studi acknowledged the theorem, and he associated it with Kotelnikov. It appears the publication was lost during the Russian Revolution, and the principle was stated by Dimmitberg. So these are all the gods of kinematics. And then here's something out of Dimmitberg's paper. So they go on and on and on, and it's a pretty hard read. But what they're doing is trying to show how that if you do take dual angles and put them into those cosine laws, you are going to get expressions that are going to be valid in 3D. And we're not going to go ahead and like dig through this and prove it. Like I put that paper up there as sort of my backstop because I have a hard time with the paper also understanding all the details. But holy cow, we definitely have something new. So what we did today is we were talking about, if we go back, so I got to wrap up, we're down to a minute left. If you go back to this mechanism, this is one of the ones that we want to solve. We're going to be given all the constant mechanism parameters and theta 5. We ought to be able to solve for the unknowns. There were four thetas and 2 joint offsets. We need to get an equation over here that has 2 of the unknown thetas. I know then I can get another equation from here in those same thetas. And then the last class, we said, well, this is how we turn the crank and solve it. So what we tried to show today is that when we do go over here, we have to develop a strategy, and there will be a strategy, but our approach is going to be to either take the vector loop equation and do a dot product with something and hope I get an equation in two unknown thetas. Or take the vector loop equation, move some of it to the other side of the equal sign, and then dot the left with itself and the right with itself, hope I get an equation with two unknown thetas. Or pick one of those cosine laws, whether they're fundamental or subsidiary, and put dual angles in and hope I get an equation in two unknown thetas. So we have to learn the strategy. That's what will be coming up in the next class. But we have three different approaches right now. And we do need to do some expansions. We need to just take a cosine. I think so we'll start with next time is just take a cosine law, not knowing if it's going to solve the problem or not, but put dual angles in and just make sure we can do it, that we can apply Taylor series expansion and work that whole thing out. Okay, dual angles, something new. I need to find out how they convinced me that I squared was -1. That's bizarre. And yet, I just take that like, like gravity is going to make my book fall. I just take it, accept it as if it's normal. So epsilon squared 0 to me is more normal than I squared -1. So if you can accept the I, then epsilon's okay. All right, weird stuff today, but we're going to start applying it next time.